physicists say that everything, even objects with mass, travel at the speed of light. See that the statement doesn't say can move at the speed of light, but it says does move at the speed of light. Sounds strange, right? However, it is a fact, but what it means is not what you think. It has a backstory involving a little mathy mumbo jumbo, and in this video, we are going to decipher that mumbo jumbo. Welcome to Physics Notebook. We are going to need a tiny little bit of calculus and tensor notation. Nothing scary, I promise. We just need to get the hang of it, so please hang on. First things first, when we say even massive objects move with the speed of light, we do not mean their motion through space, rather the motion through space-time. Chances are you already know that in relativity, space and time are not two independent entities. They are intermingled into a single thing called space-time, an arena where everything occurs. In an earlier video in this channel, we have elaborated on this idea. You may give it a try, it's a fun watch. Anyway, when we see an object move through space, we also see time ticks along as the motion takes place. So I guess it won't be unfair to say that objects move not only through space but also through time, or in other words, space-time. How do we describe this motion? Simple. We, as observers, keep the record of the object's spatial location as per our XYZ coordinate system at every instant of time as shown by our clock. These time readings shown by our clock is called coordinate time. So we have a chart of XYZ, the object's spatial coordinates, versus coordinate time t. So you tell me when and I can tell you where to find the object. The technical way of saying it is we know the position coordinates of the object as functions of the coordinate time t, written as x of t, y of t and z of t, and similarly its position vector as a whole, if you like the vector notation. Now the moving object, if it has mass, also has a clock of its own, one that is moving with the object and therefore is the rest frame clock of the object. Time shown by this clock is called the proper time, usually denoted by the symbol tau. Naturally, this clock also ticks as the object moves, but at a different rate than the clock we observers use. Why? Because it is a fundamental fact of relativity that two clocks that have relative motion, like in this case, tick at different rates. Okay, so how is the coordinate time t given by the observer's clock, that is our clock, related to proper time tau given by the object's clock? By the famous time dilation relation. I know it looks a bit scary here because of the integral signs, but trust me, this is the actual formula of time dilation. The equation that you see in most relativity textbooks applies for the constant relative velocity, which is only half the story. We have quite a few videos on time dilation and its various implications involving scenarios of non-uniform velocity in this channel. Links are in the description, you're welcome to watch them. Anyway, now we have the object's position coordinates as functions of coordinate time, and then also coordinate time as a function of proper time tau. Thus, effectively, we have the object's position coordinates xyz and time coordinate t as functions of the proper time tau. Collectively, these are called the space-time coordinates x mu. Now, mu is called the index. It just helps us keep track of the specific components. For example, mu equals 0 stands for the time component x0 equals ct. Mu equals 1 stands for the x component of position. Mu equals 2 stands for y component of position, and so on. For the time component, we use ct instead of t here to make all the four coordinates have the dimensions of length. Remember, this does not convert the time component into a space component. It just helps us give it the dimension of length, allowing us the liberty to do mathematical operations like addition, subtraction, etc. conveniently. Alright, what does this set of functions x mu for all the tau values represent physically? The trajectory followed by the object through space-time, otherwise known as the whirl line of the object. In the pedantic language, it is a parametrized curve with the object's clock time, the proper time tau, acting as a parameter. Successive values of the tau parameter will take you to all the space-time coordinate points or event points that the object is moving through. With the whirl line of the object mathematically depicted as a parametrized curve that traces out the object's motion through space-time, we are now in a position to define the velocity associated with this motion. Since we are talking about motion through the four-dimensional space-time, not through the usual three-dimensional space, so the associated velocity is not the ordinary velocity vector v with three spatial components vx, vy and vz. Rather, it will be something new with four spacetime components. We call it the four velocity. You see, four components, so four velocity. We define four velocity exactly the way we define our good old three-dimensional velocity vector. How do we define the velocity vector? dx dt, right? But what is dx dt operationally, geometrically and physically? If you know the trajectory of the object through space, it means we know the object's three-dimensional position vector x for all values of the coordinate time t, or in other words, as a function of the coordinate time t. This trajectory, that is the trajectory through space, is also a parameterized curve with coordinate time t as the parameter, just like the world line of the object was a parameterized curve with the proper time tau as the parameter. Now dx dt is basically taking derivative of the vector function x with the parameter t. Physically, it means calculating the rate of change of the position vector of the object with change of time t at any given instant, all done according to the observer's clock reading or coordinate time. Geometrically, it represents the tangent vectors to the trajectory followed by that object through space at different coordinate time values. Exactly in the same manner, the four velocity represents the tangent to the world line of the object. We calculate it by taking the derivative of the four functions x mu with the corresponding parameter tau, the object's rest frame clock time or proper time. To keep track of its four components, the four velocity also carries the same index mu, just like x mu, and we use the symbol u mu for it. Okay, does it have anything to do with the three-dimensional velocity vector? Of course it does. U mu is dx mu d tau, right? We can use something called the chain rule in calculus to re-express it as dx mu dt multiplied by dt d tau. Now dt d tau can be calculated from the time dilation formula. Turns out it is just the inverse of the square root of 1 minus v by c squared, that is the Lorentz factor gamma. Of course, the velocity vector is not necessarily a constant here, so the gamma is also a function of time t. How about the other factor dx mu dt? We just have to break it down into its four components to see what they are. For mu equals 0, it is dx0 dt or c dt by dt, so just see the speed of light itself. For mu equals 1, 2 and 3, it's dx dt, dy dt and dz dt, the three components of the three-dimensional velocity vector itself, which can be time varying if the particle is moving with a non-uniform velocity. So the four components of the four velocity are u0, that is gamma c, and ui, that is gamma vi, while vi means the three components of the three-dimensional velocity vector. All of them may or may not be varying with the time in general. Okay, so enough of the calculus and tensor mumbo jumbo. Where is the part where this massive object is going to move with the speed of light? Well, look at the components of u mu, that is gamma c and gamma v. What would their values be from the object's perspective? I mean, in the object's rest frame? Obviously, the object appears to be at rest, not moving along the three spatial directions at all. So all components of the velocity are 0 at all times. So the three spatial components ui, which are gamma times vi, are 0 too. But look at the 0th component. For v equals 0, gamma becomes 1, so u0 is just c, the speed of light itself. So this means in the rest frame of the object, it moves along the time direction with the speed of light. Agreed that the time direction is not a direction in space, so motion along it is hard to imagine. But after all, we are talking about the object's motion through the four-dimensional space-time, not through space. And in there, time direction is indeed a valid one. There is another way of showing this, by calculating the magnitude of the four velocity. Now, how do we do that? Remember space-time interval d squared between two infinitesimally close events p and q? If event p occurred at time instant t at a spatial location xyz, using our index notation we say p has spacetime coordinate x mu. Then event q, being infinitesimally close to p, has only a slightly different spacetime coordinate values. That would be, say, x mu plus dx mu. Now this dx mu, the difference in the spacetime coordinate values, is a 4 vector. What is a 4 vector? Some other time, guys, okay? For now, Think of it just like our good old 3-dimensional position vector, but with one extra component since it is in the 4-dimensional spacetime. Now, the spacetime interval ds squared is actually the magnitude of this dx mu 4 vector. To calculate it, we take the square of the time component dx0 minus the sum of the squares of the space components. That gives us c squared dt squared minus dx vector squared. If you recognize it, great. If not, you should watch my earlier videos on spacetime interval. It's kind of a big deal in special relativity, so link is in the description. Anyways, like dx mu, the 4 velocity u mu is also a 4 vector. So magnitude is computed the same way. Square of the time component minus the sum of the squares of the space components. We know their values in terms of gamma c and gamma v, right? So if we plug those in and simplify using the expression of the Lorentz factor gamma, we'll get c squared. Funnily enough, this magnitude is always c squared, no matter what the value of the normal 3-dimensional velocity vector is. This also kind of demonstrates that the 4 velocity or overall velocity of the particle for its motion through the spacetime is always equal to the speed of light. Notice, from this spacetime perspective, the issue is not if an object with mass can move with the speed of light, but that the object has to move with the speed of light. Pretty dope, right? So that's it for this video. Let me know how did it go with a tiny mini bit of tensor notations this time. Does it still feel like mumbo jumbo? Fire up the comment section. I'm all ears. Also, if you have not seen the video on spacetime interval, it is right here on the right. Video on the proper time versus coordinate time is on the left. See you in the next video. Bye bye.